this kind of behavior. Oh, we hadn't put it on?
Now I put it on.
Oh, I'm sorry. Yes. Thank you. Okay. Okay. So I'm going to just try to first examine what happens in the Hart catchment limit, and then try to see if we find Reggio behavior in the Reggio. Okay. Oh. Okay, let's start with the closed string formulas. What we're going to do is to take very large, S, T, and U to be all very large. Okay, so now when we do that, we're going to use this famous approximation for the gamma function. The famous approximation is that gamma of x is equal to x to the power x times e to the power minus x. E to the power minus x. And then there are some connections. 1 by x. That's it? Okay. Excellent. Excellent. This will be some leading for us. Okay. So now let's apply this formula and ignore these terms because there will be power law and the exponent. We find that this term cancels with this term. Okay. So let's apply this formula up here. Okay. So what we have is root x upstairs. Root x. Yeah. I'm not going to care. Okay. So let me numbers and algebraic functions are not going to care. Okay. So. Okay, so let's apply this formula to each of these cases. Okay, so we have minus alpha prime s by 4 minus 1 to the power minus alpha prime s by 4 minus 1. Okay, and then we have, so first I'll just do these parts. Okay, and then go over considering the points. Okay, so right. So there's this, and then the other x dependence is alpha prime s by 4 plus 2 to the power alpha prime s by 4 plus 2. And we have similar things for t and u. Okay. Now, now there are two things. See, firstly, there is this guy has a minus sign, this guy has a plus sign, but that's just minus 1 to some power, some phase. Forget about it. So, if we're interested in modulus. So as far as modulus is concerned, this is alpha prime s by 4 plus 1 to the power some large power minus alpha prime s by 4 plus 1, and then alpha prime s by 4 plus 2 to alpha prime s by 4 plus 2. Okay. Now, what I'm going to try to do is to combine these two things together. So for that, I need to shift the argument of one of these. Let me shift the argument of this. So I'll call this alpha prime s by 4 plus 1 plus 1. Okay? And then I'll write that as alpha prime s by 4 plus 1 into 1 plus 1 by alpha prime s by 4 plus 1 to the power alpha prime This is to the power alpha prime s by 4 plus 2. And this is to the power alpha prime s by 4 plus 2. Now, when I take the limit of large s, what does this become? It becomes an e. And it's one of the classic formulas for e, this number, which is almost 3, which is that 1 plus 1 over n to the power n, limit n goes to infinity, is e. And that's basically what we've got. Okay? So this is some number, some constant number, which instead of throwing away 2 pi is being thrown. Okay? Okay? So this is not doing anything. So what that means is that you can just replace this plus 2 by plus 1 at the level of precision by working and combine powers. Okay? So when we do that, all that remains is 1 over alpha prime s by 4 plus 1.
The top one is negative, the bottom one is positive, the powers.
Sorry. Yeah. Yes, of course. Sorry. Yeah, just one. Yes. Yeah, okay, let's just keep that much. Okay, so you're right, thank you. So this thing is alpha prime s by 4 plus 1 to the power minus. Yeah, and then this 1 and 2 we can ignore because those are power law corrections. So minus alpha prime s by 2. Okay, here also. So alpha prime s by 4 to the power minus alpha prime s by 2. And so what we get. No, maybe this is right. Maybe I said it wrong. Fine. So the next answer then is e to the power minus alpha prime s by 2 and then log of alpha prime s by 4, okay, plus alpha prime s by t by 2 log alpha prime t by 4 plus alpha prime u by 2 log alpha prime u by 2. Perfect. Perfect.
Are we depending on the explanation of this?
So we're trying to, if as long as we get e to the power minus s log s, we're keeping them common into piece. Exponentially come to it. Okay. Yeah. No, this is exactly what questions he gets. Right? Okay. Now. Okay, now the next thing that Kulczynski does is evaluate this as a function of momentum and angle. So let us do that. he gets this formula, then he doesn't have an S log S term in the end. Let's just see. Okay, so we'll do the kind of exercise we did last semester. Okay, so we've got K1, K2, K3, and K4. There's some angle theta here. And in terms of theta, I want to compute ST. Okay, so S was simply K1 plus K2, the whole thing squared. But suppose K1 was in one direction, so it was P, so energy P00, okay, and K2, so that was K1, K2 was equal to energy minus P00, K3 was equal to minus energy, we're in the center of mass, right? Minus energy, outgoing this reverse sign, so minus P cos theta minus P sin theta 0, and K4 was equal to minus energy plus P cos theta plus P sin theta and 0. Okay, so the physical momenta of K1 and K2 are these, and the physical momenta of the outgoing particle are minus of this. Okay, then let's very quickly compute S, T, and U. So S is of course 4 P squared, right? T, which is equal to P1 plus P3, the whole thing squared with a minus sign, is equal to, so P1 plus P3. So the energy is cancelled. So that's right. So it's P squared into 1 minus cos theta the whole thing squared, which is equal to P squared 4 sin squared theta by 2. Well, thank you. Thank you. 1 minus cos theta the whole thing squared plus sin squared theta, which is equal to P squared into 4 sin squared theta by 2 plus 4 sin squared theta by 2 cos squared theta by 2. Okay, which is equal to, and then we take sin squared theta by 2 out. That was a nice formula, right?
First we simplify 1 minus cos theta square plus sin theta square, which is just 2 minus 2 cos theta square. 2 minus 2 cos.
P squared into 4 sin squared theta by 2. Sorry, you want to do something different from this?
1 minus cos theta square plus sin theta square is basically sin square theta is basically.
Oh, yeah, that's what I have. Yeah, thank you. Thank you. Which is a P squared into 1 plus 1, so that's 2 minus, so 2 to 1 minus cos theta. That's what we said, right? Which was equal to 4 P squared to sin squared theta by 2. So all I were getting the same thing. I probably was. That was sin squared theta by 2 square. The way I did it, I said I had a 1 minus cos theta, that was sin squared theta by 2, and then I was supposed to square that. So then that would have been sin squared theta by 2 plus cos squared theta by 2. What? Okay. Yeah. Okay. Excellent. So that was P, and U is the same thing with, Mangesh's nice method will tell us that U just flips the sign of this thing. So this becomes cos. So U is equal to 4P squared cos squared theta by 2. Okay. So now we're going to plug into e to the power minus s alpha prime by s alpha prime by 4 log S alpha prime by 4 plus similar things. Okay, so we're going to plug that in with these formulas. So, what do we get? For S, we just get e to the power minus e squared alpha prime log e squared alpha prime. Right? That was the S component. So let me just try to think of what appears in the exponent. Minus alpha prime.
Shiraz, sorry, T and U will have an extra minus sign because the definitions were minus P1 plus P2 square, which was perfect for S but
Yeah.
for T and U.
Thank you. Thank you. Excellent. Okay. So now because times log of alpha prime
The other coefficient was
plus 2. So I should put 2 here. Okay, excellent. So that's what we get from this term. I'm carrying the minus. So now the other terms will have a plus. Okay. So this will be plus 2p squared alpha prime sine squared theta by 2 log of alpha prime p squared sine squared theta by 2. Right? Plus 2p squared alpha prime cos squared theta by 2 log of alpha prime p squared cos squared theta by 2. Now, in the very high energy limit, E squared and P squared are approximately the same. Okay. So, in the very high energy limit, we can rewrite this as 2E squared alpha prime into minus log alpha prime E squared plus sine squared theta by 2 log alpha prime p squared sine squared theta plus cos squared theta by 2 log alpha prime p squared cos squared theta. Okay, good. Now you see this log can be split up into log alpha prime p squared. This I'm replacing by e squared. Log alpha prime e squared plus log sine squared theta by 2. Okay? So then we get the terms with log alpha prime e squared come to minus 1 plus sine squared theta by 2 plus cos squared theta by 2. So they cancel.
It's not mass effect, we're talking about techniques.
What?
We're talking about techniques.
Yes, yes. But we're at very high energies.
Alright.
So the difference between E and P is negligible. Okay? So the terms which are E squared, log E squared, effectively cancel. So what remains? Is 2E squared alpha prime into minus 1 plus sine squared theta by 2 log sine squared theta by 2 plus cos squared theta by 2 log cos squared theta by 2. In fact, this minus 1 is not that, because that was the thing that cancelled with that. This is just this. Okay, and this matches exactly what Wilkinson has. Okay? So what's the lesson? The lesson is that at very high energies and at fixed angles, our scattering amplitude decays exponentially fast in S or in E squared. Okay? Now, this is actually an important thing. Why is it important? It's important because it's very different from what we see for scattering with Einstein. we do classical scattering with Einstein gravity. Okay? We do classical scattering with Einstein gravity just because the Einstein vertex operator is too derivative. Okay? The scattering amplitude grows like S, like energy, and therefore the probability squared grows like S squared. Okay, but we look at amplitude says it grows like S. Okay? So the Einstein scattering amplitude grows with energy. This is just the fact that the gravitational force is stronger at high energies. It's Newton's law, right? G mm by r squared. You increase m, which is energy, you increase the force. Or you decrease r, which is the same thing as increasing the energy, you increase the force. Okay? So, the Einstein, classical scattering in Einstein theory leads you to suspect that scattering amplitudes grow larger and larger and larger. Okay? And we could debate about what happens when quantum effects enter. Here we have not included any quantum effects. We're just doing classical scattering once again, but in string theory. And what we say is that when E squared becomes much larger than alpha prime, E squared becomes much larger than alpha prime, that growth, which would have, by the way, have been there had we been calculating graviton rather than tachyon scattering, and had we kept track of prefactors. This is just some power law. We've not kept track of those things. The growth would have been there. We would have seen something growing, like a power, and then being cut off by this exponent once E square reaches string scale. Okay. Now, what is the basic reason for this? I am just going to give you very quickly basic intuitive reason for this. You see, the basic reason for this is the same reason that led physicists in the early part of the last century or late part of the previous century to suspect that if you took electrons and scatter them off an atom, what you would find is a very small scattering amplitude at high energies. The basic reason is that of form factors. So let me give you 2 minutes of quick intuition. In non-relativistic quantum mechanics, there is this rule called Fermi's golden rule or something like that, which tells you that the leading order in perturbation theory, if you want a scattering amplitude of a particle of some potential, then the answer is just given by the Fourier transform of that potential at the momentum, which is momentum exchange. Okay? So suppose you've got k coming in and p going out. Then what you're supposed to do is e to the power I p minus k dot x v of x dx. This thing is supposed to give you the scattering amplitude. This you all remember from your quantum mechanics courses. Okay. Now, so scattering amplitudes at leading order are related to Fourier transforms. Okay? We're looking at high energy fixed angle scattering, so P minus K is some very large number. So what we have to do is to ask, how does a Fourier transform of, so suppose this potential was non-zero over some typical length scale alpha. How does a Fourier transform of this be? Well, to get an example, let's take V to be a Gaussian. If V is the Gaussian in position space of thickness alpha, then it is a Gaussian in momentum space of thickness 1 over alpha. Okay? So, suppose V was e to the power minus x squared by alpha squared by 2. The Fourier transform will give us a scattering amplitude which goes like e to the power minus p minus k the whole thing squared, alpha squared by 2 by 2. I mean, not by 2 is right. Okay. What is the main point? The main point is that as p minus k, this momentum is taken to be very large compared to the length scale inherent compared to the moment inverse length scale inherent in the problem, the scattering amplitude rapidly decays. Okay? This reflects the fact, a general fact about physics, that if you've got objects of different, if you put different length scales into the problem, they don't directly interact very much. Okay? So the thing that we were scattering was, let's say, an electron. The inherent length scale of the electron, which is 0. But because of quantum mechanics, there's an effective length scale associated with the minimum size of a wave packet, which is set by the momentum exchange in the problem. Okay, so you've got a little electron lump. Effective dynamical length scale is 1 over p minus k mod, let's say. You've got this big fluffy cloud. When this becomes much smaller than that, it just zooms through more or less without seeing it. Okay, and this effect is, you see, all over physics. And sometimes it's called the effect of a form factor. The effect of scattering, because one big fluffy guy doesn't affect a much smaller guy. Okay? This, was what Rutherford expected to see when he did the scattering of electrons of atoms. Because the wisdom at that point in 1910 was, or 11 or whatever it was that that's what an atom was like. It was a big, fluffy something or the other. So he expected to see small deviations of these electrons. That's not what he saw. What he saw was most of the electrons didn't do anything. But once in a while they did boom. Because they were not scattering of this big fluffy electron, the atom, they were scattering of the small compact nucleus. Okay? And this is, one of these classic things that, can you imagine, just 100 years ago, just 100 years ago, we thought atoms were these big fluffy things. That's how much we learned. It's amazing. So this is one of these classic experiments that changed the course of physics. By the way, there's this, Rutherford was in this famous Solvay conference, you see photographs on. Rutherford was one of the participants in this famous Solvay conference, and he'd just done his experiment, maybe a few months before. But that experiment was totally ignored in that meeting by everyone, including Rutherford. They were at the cusp of a great revolution of physics. They were all the best minds of Einstein and all of those guys, and they just totally didn't get it for a while, of course. That's often how it is. Something really important has happened. It takes a while for you to understand it. Anyway, so just getting back to string theory. So what we see is this soft form factor. Now, basically what's going on here is this, that the string is a big fluffy object whose size we begin to see. When we do scattering at energies small compared to the string scale, you don't get it. The string can be treated like a point particle. But when you go to energies very large compared to the string scale, okay, you see what Rutherford expected to see but didn't see. That is the softening of the scattering amplitude, because you're probing an object of huge, an object that's big and fluffy, by a much smaller length scale, a much higher energy scale. Okay? So it's basically this effect, okay, that is giving us the softening of the string theory. So the reason that string theory scattering amplitudes classically, there's no funny loop effects, emphasize that, classically are so soft, the fundamental reason for that is that the string is an extended object. Okay? Of course, the miracle of the whole thing is that you have an extended object which at low energies gives you ordinary point-like gravity. And that gives complete consistency with everything. But just the fact that string scattering amplitudes become soft, in some sense you might have intuitively expected it. Just by the fact that string is an extended object, its size is set by alpha prime, that sets the softening.
Sorry, isn't this a little different from that scenario because you have two strings that are coming towards each other, so then there's in a way there's some missing. The probability of the scattering from each other would reduce because they're at higher velocity. So
Sorry, I didn't understand.
I'm meaning it's not that there's one string that is going to a fluffy ball, right?
It doesn't matter. See, even in that situation, you see non-relativist quantum mechanics, you can have one particle scattering off another. Then you move to center of mass coordinates. It's the important thing is what is the interparticle interaction potential. Okay? Now if you have two strings coming together, the interparticle interaction potential is big and fluffy of order the strings. That's all that we're seeing. Yeah. Okay? And that's clear, right? If two big guys come and they overlap themselves. Yeah. Okay. Excellent. So far so good. Let us also quickly any questions or comments about this?
So the reason why in GR at tree level the amplitude reduces to gravity of gravity is it because it's basically a point particle up to the max?
Correct. So there's this softening effect you just don't see. Of course, now once you start taking quantum effects into account, who knows what happens? Except we don't have consistently do it. Yeah, exactly. The image just classically gets softer. Fantastic. Let's move on to a quick consideration of this regime. This regiment. Okay, so once again the formula. This time we have to be much more careful because the final answer is going to be a power. So we can't throw away powers. T by 4, 1 minus. Oh, and by the way, no, none of you asked this, but you could have asked, since, you see, my logic for keeping the first term in the Stirling approximation was that I kept the term that was s log s, s to the power s, which in the exponent is s log s. But then we saw that the s log s terms actually cancelled. All we were left with was just the e to the power minus s. So you might wonder, what about the second term in the Stirling approximation? That's also naively of the same order. Why aren't we keeping that? And can you see immediately what the reason for that is? What? S plus t plus u. Exactly. It looks like there's such a term, but both in the numerator and in the denominator, those terms actually cancel out. Because s plus t plus u is equal to some constant. Okay? So that second term did not contribute a piece proportional to e to the power minus s. All of the contribution came from the first term. Okay. So we have minus alpha prime u by 4 minus 1. Okay, gamma of minus plus alpha prime s by 4 minus 2, gamma of alpha prime p by 4 plus 2, gamma alpha prime u by 4. Now we're taking the limit s going to infinity, u going to infinity, but t had fixed. Okay? Now we have alpha prime into alpha prime by 4, s plus t plus u is equal to minus 4. So in particular, alpha prime by 4, s plus u is equal to minus 4 or minus alpha prime t by 4. Okay? So now we have two terms here that just depend on t. Those just stay. Okay? Because we're not doing anything to t in the limit, we're just taking the simple numbers. So we've got gamma of minus alpha prime e by 4 minus 1 over gamma of minus alpha prime e by 4 plus 2. They're there, but of course they're also independent of x. They're not going to give us this, they're not going to contribute to this leading rate. Here, s to the power. It's just a prefactor, no way. The interesting stuff comes from these steps. Okay? So, now we have to be a bit careful. So let's look at these terms. Once again, we use the Stirling approximation, but keeping terms all the way up to the power. And the Stirling approximation for that is x to the power x, e to the power minus x, divided by square root of 2 pi x. So gamma of m, m to the power m, e to the power minus m. Okay, this is the formula that one.
Upstairs, root 2 pi was
Upstairs?
sorry. Root 2 pi was
You're right. Okay, so now let's evaluate all those terms carefully. So we get minus alpha prime s by 4 minus 1 to the power minus alpha prime s by 4 minus 1 e to the power alpha prime s by 4 plus 1 2 pi m really, but I'll keep m this, and then alpha minus alpha prime s by 4 minus 1 to the power half. Okay, that's the first. Then we have divided by, let's do the second term. Alpha prime s by 4 plus 2, alpha prime s by 4 plus 2, e to the power alpha prime s minus s by 4 minus 2 into alpha prime s by 4 plus 2 to the power half. And then exactly similar terms with s replaced by e. Okay. Okay. So now let us try to estimate all these terms. Let us try to estimate all these terms. What's the strategy? Firstly, the difference between this plus 2 and the plus 1, once again is just an e independent of s which I throw away. So I'm going to replace this guy by, I'll just drop these constants here. Okay? Phases I'm dropping. Okay? So,
When those constants in the exponential?
no, those are powers.
Okay, so and e is coming actually from the approximation of the denominator alpha from s by 2 plus. There was an e coming out.
But it was just an e, independent of them.
You should also about the 1 plus 1 and minus 1 e
in the
power.
exponential 1 and 2.
Here.
No, the next exponential.
Ah, yes, that one. Absolutely. Yes. Excellent. So now what we get is alpha prime s by 4 to the power minus alpha prime s by 2 minus 3, and similarly we get alpha prime u by 4 to the power minus alpha prime u by 2 minus 3. Okay, and then we will get times e to the power minus alpha prime s by 2 minus alpha prime u by 2. Thank you. Okay. Yes.
Stirling approximation is valid when the modulus of the argument
Is very crucial.
there's no like sign.
There's no sign. It's a uniform approximation. I can prove that by using integral. These integral formulas for gamma functions are overall complex plane. The Stirling approximation comes by doing this ideal point. One of these integral formulas, which just control formulas. Okay. Excellent. Now, so let's once again, and I've got to keep track of these. And those cancel, right? Okay, very good. Excellent. So let's once again write this as e to the power alpha prime s by.
Last one is just minus alpha prime t by u.
Oh, excellent. So this is. Thank you. So that alpha prime s by 4 minus alpha prime s by 2 minus 3. Alpha prime u by 4 minus alpha prime u by 2 minus 3. And this is some function of t. Right, as you said, we absorb this into the t. This gets absorbed into t. So I put the extra factor of e to the power minus, what is it?
Alpha prime
Minus 8 plus alpha prime minus alpha prime p by 2. Something like that. I'm just using
Are we considering those e raised to minus 8s?
e to the power minus what?
8, because that is also constant.
Okay. Fine. Whatever it is, we put it in there. We're not interested in it. Excellent. So this is what remains. So now we will once again evaluate this as e to the power minus alpha prime s by 2 minus 3 into log alpha prime s by 4. Okay. Minus alpha prime u by 2 minus 3 into log alpha prime u by 2.
Plus 3.
Plus 3. Thank you. Okay? And, okay. Now, in order to simplify this, once again, let's use the let's use the representation, the formulas for S and U in terms of scattering. So S was equal to 4e squared and U was equal to 4e squared into cos squared theta by 2. We'll remember that P was equal to U was equal to the minus 4e squared the sine square theta by 2. Okay, so let's plug this in. So we've got e to the power minus alpha, e to the power minus, then alpha prime 2e squared plus 3 into, I'll just keep track of it once again, just the argument of the explanation. Alpha prime 2 alpha prime e squared plus 3 log e squared alpha prime plus overall with the minus and then minus 2 alpha prime p squared plus 3 log alpha prime p squared. Except that here we have cos squared theta by 2 and here we have cos squared theta by 2.
Wasn't this the limit in which theta is near 0?
Yes, it is.
So it's cos square.
Yeah, exactly. So now, since we're taking t held fixed, what we have is for p theta is p squared theta squared. Okay, p is going to infinity, theta is going to 0. So p squared theta squared is held fixed. So in fact, what we have is that in this limit, p squared theta squared minus p squared theta squared is equal to t. Okay, so theta squared is equal to minus t divided by p squared. P squared, e squared also. Yeah. Okay. So theta is equal to minus t divided by e squared, and so cos square theta is equal to 1 minus 1 plus t by 2 e squared. Okay, t is negative. That's why it's 1. Okay, so we'll just plug it. Okay, so now we have minus 2 alpha prime e squared plus 3 into log of alpha prime e squared. And I just have a sign here. You had an opposite sign. This, I got this side wrong, right? Minus. Sorry about that. Minus of minus 2 alpha prime e squared into 1 plus t by 2 squared plus 3 alpha prime e squared in 1 plus t by 2 e squared. This will play about the t by 2 e squared. Okay, good. So we are almost at the end. Well, this guy.
No, you can't forget about 1 plus 2. You have to put, you have to do the first order expansion. It will contribute in the same order as the t that's already there.
Maybe you're right. Maybe you're right. 1 plus, thank you. Thank you. E squared, sorry, what was this?
It will be log alpha prime e squared plus t by 2 e squared.
E squared plus t by 2.
No, t by 2 e squared also is log alpha.
Sorry. What was this originally? It was log alpha prime u, and u was had this factor. So it was just this factor multiplying alpha prime e squared. Yeah,
e square and t have the same.
right. E squared and t have the same dimension. Yeah, this looks right. Thank you. That's it. That's probably it. Yeah. So this we just expand as you said as minus 2 alpha prime e squared plus 3 into log alpha prime e squared, and then both these terms will expand. So one term here. See this minus 2 alpha prime e squared into this leading order piece cancels this piece. Okay, so that goes. What about the plus? The minus 3 and the minus 3 just add up. Okay, we get minus 6 alpha prime e squared minus 6. Sorry, times log alpha prime squared. and then suddenly if you take the correction from there, that's something. Okay. Then there are the contributions because we take this guy. So the e square cancels, and we get now minus into plus, minus into minus, so plus. So and the 2 cancels alpha prime t plus alpha prime t. Correct? Okay. And then from here we just take this will be so now this log we expand as so we have a factor of 1 plus x, so x is p by 2 e squared. So we have a term that is p by 2 e squared into this leading order guy here. So that is plus alpha prime e square. Plus alpha prime, yes. So it becomes plus 2 alpha. Okay. The fact that both Now this p was multiplied by a log, both were multiplied by log. Log alpha, right? Yeah. Excellent. Excellent. Okay. So now we've got this log alpha prime e squared in the exponent, which is just s downstairs. Okay? So this thing is s to the power minus 6 plus 2 alpha prime. Okay? And I think we probably want to write this in some funny way. Let me see. Okay, you can open string. Sorry, just trying this. It's formula. Oh, just very good. He doesn't have this.
So where did you get the factor 2 from in front of?
The 2 because of 2 terms.
Why should you divide it by 4 for
What?
S is 4 e squared.
S is 4 e squared. That's fine. That will. Whether it's S or S by E. Yeah. No, it's this. He's getting the same 2 alpha prime t. But the 6 he's getting as 2.
The function of t that we left out had some exponential minus 8.
No, but it didn't have an S in it. We're only interested in the power of S. I've got this power of S with a minus this thing. Oh yeah, I'm sorry. He is getting S to the power 2 alpha prime t minus 2. Wait, minus 2 minus. It's so confusing because he keeps defining things all along the way. He's getting e to the power. Yeah. Minus alpha cp. What the hell is alpha cp? I think it's
Different rate of the both different
alpha
c is 1 plus alpha prime x upon 4.
1 plus alpha prime x upon 4. So he's getting, I think he's getting 8, not 6, yeah. He's getting a different number of days. Okay. I'm going to leave this. Hey, we got the journey club anyway. I'm going to request you. I've made some mistakes. The important point, of course, we see. that is s to some power, which is a function of t. That function of t basically carries information of the string slope. This is sometimes called a Regge trajectory. Maybe at the beginning of the next lecture, I'll give you 2 minutes of the interpretation of this quantity. And then we'll move on to the study. Okay, sorry, it's a bit of a boring lecture. It's not much, I mean, we're just expanding. Okay.